Hi all, so today I would like to introduce our final unit of multivariable calculus, which is vector calculus. And in today's video, what we want to do is introduce the notion of a vector field, which will really be fundamental to our study of calculus with vector fields. So we have, we know what vectors are. We still kind of need to discuss what a field is. But once we know both of these things, then we're fully prepared to look at what a vector field is and what we're going to be doing with vector fields. What we want to do with vector fields is we want to look at calculus of vector fields, and we want to apply all of the tools that we've been learning in the past 4 units to apply it, right? So we're going to look at parameterizations, we're going to look at partial derivatives, we're going to look at integrals, right? One of the prime examples that is really the capstone of all of calculus, we call it the divergence theorem, and it'll be one of our final topics. But it considers, say we have a vector field, and say we have some volume like this, which we call V or something. It's asking if I have a vector field that describes motion of, I don't know, fluid or electricity through that, what is that rate of volume flux, right? And so what is the rate of this going through there? And this is, of course, modeled by a vector field, but we're going to discuss what that actually means now. So I don't need to go super deep into this because it really is a fairly simple concept, a vector field. A vector field essentially is a function that assigns each point, xy, to a vector, f of xy. So what do I mean by this? This is the two-variate case here. But if I have a coordinate plane and I have a vector field, f, and f assigns each point xy to a vector, and I might have something that looks like this. Here I'll have a vector there, 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 I'll have a vector there. I'll kind of have a vector everywhere, right? So if I have a vector here, a vector there, maybe the vector points radially outward. That could be interesting if this modeled velocity flow of a fluid or something. You might think, okay, there's some sort of source here, like a spring or something that's having all of this water leave, modeled by this vector field. Or electricity, you could have like a monopole or something like that. Anyways, what we want to look at is we want to look at calculus of these vector fields. And these vector fields describe motion macroscopically, and we want to determine how that motion changes, how to find important quantities with that motion, and overall just learn more about the motion of a vector field. So again, in simplest terms, a vector field assigns a point, or assigns a vector to a point, okay? That's fairly easy. Now, you can have multiple vector fields, and you can model them by different functions. So x, the direction of the x vector might be a function of x and y. The direction of the y vector, the magnitude of the y vector, might also be modeled by a function of x and y, or the y component. The components can be modeled by different functions. So you could have the vector field f is equal to, I don't know, maybe sine of x, xy times I hat plus e to the ln cotangent of z j hat plus x squared y cubed z to the 6th k hat. That's an example of a vector field. It's obviously one that we don't really want to draw out. We can have computers for that, but that is a vector field nonetheless. We have a component for each direction. This is the idea of a 3-dimensional vector field. So a 3-dimensional vector field might model like fluid or something like that, or it could really model anything. So if you have an example, you can consider fluid flow, obviously. You can consider electricity flow. You can consider the motion of, or the effect that gravity has on a planet. So if you have a planet here, or something like that maybe, and then you have a little rocket ship or a little moon there, so say that's the moon and this is a planet, you might have big vectors here that point in because the gravitational field of this star is going to be very strong. Then you might have vector fields that are kind of a little smaller for the moon, because the moon doesn't have as much mass, so it wouldn't be as heavy and it wouldn't attract as much. You might have vectors out here that are very small that might say, okay, well, we're kind of far away because gravity is an inverse square law, so they're going to get smaller and smaller proportional to the inverse square. And you might be in the middle of the two planets. You're thinking, okay, well, I might start being pulled very, very slowly towards this planet and then faster, then faster, then faster, then faster. You obviously model that with the vector field here. It's obviously not well drawn, but it is nonetheless a vector field. Anyways, in the next video, I want to discuss the concept of a gradient field, and then we will be kind of moving on to the calculus of it. So one of the main ideas that we have here is, say, this is one of the things we'll really be looking at. Say I have a force that's modeled by a vector field, and I want to pull a mass in some arbitrary path around that force field, and we call that path C. Well then, how do I find the total work done? So I have a vector field in this two-dimensional space. My path is also, well, it's one-dimensional, but it's it is curvy, so it would be two-dimensional in some respects. And what you want to do is find the work. So what you actually need to do is all the parameterization stuff comes back. We actually take this almost as a single variable integral. You can think about the vector field being kind of a surface or something, and you're taking this function, or you're taking this curve, you're finding the area under it, but three-dimensionally. So consider like a three-dimensional area popping out of this curve, and you're trying to find that integral. It's pretty complicated, but we will learn it in due time. Thanks for watching. We'll see you next time.